So now that we've established this particular cycle, we could do this for other cycles as well, but let's look at what's happening here in terms of the first and second laws of thermodynamics. So first we can look at delta U for the engine. We know that overall this has to be equal to 0 for the whole cycle. If we go from 1 to 2 to 3 to 4 back to 1, because internal energy is a state function and we end up back at the same state we started in, we know that's equal to 0. And so that also has to be equal to the work done by the engine plus the heat exchange. So our reversible heat exchange, right, this is all done reversibly at the hot reservoir plus the reversible heat exchange done at the cold reservoir. All right, the other thing we know is that the entropy change overall for the engine also has to be equal to 0 because it's also a state function. And so we can say that dq reversible h, I'm probably going to start dropping the reversible part of that over t, and this is th, plus dq reversible at the cold reservoir divided by tc. One thing to note is that this is a positive value, and this is a negative value, right? So heat goes into the engine, so it must be positive, it increases the internal energy, and this is heat leaving the engine at the cold temperature. Okay, so that gives us, from this equation, we can get a relationship between the work, the minus work of the engine is equal to the sum of the, I'm just going to write these as QH and QC. They are the reversible heat, of course, because this is all done reversibly. Okay. And that gives us some equations that we can now work with. All right, so what's the efficiency of the engine? So, our overall process is we're taking heat in, doing some work with it, and heat going out. So, in the maximum efficiency would be that we take all the heat that comes in at the hot reservoir and all of it leaves as work. That's impossible, but that's sort of like would be the the fairyland, so we could do that. So the way we define efficiency is equal to how much work did we get out divided by how much heat did we put in. And so we can go ahead and substitute our expression up here into this equation and say, okay, my negative work is QH plus QC divided, and then that's divided by QH. Okay, so we've gotten something interesting here, but the other thing we can do is use this delta S equation here to now do things in terms of temperatures. We know that the QC is equal to negative QH, just doing some algebra here, times TC over TH. All right, and that just comes from rearranging this expression here. Since that's equal to 0, QC over TH is equal to QH over TH is equal to negative QC over TC, and then we can rearrange that into this expression here. So if we plug this in to here, we can write everything in terms of QH and temperatures. So we'll get QH plus, not plus, minus, QH times TC over TH divided by QH. But now we have a bunch of QH's, those all cancel. And so overall we just get the efficiency is equal to 1 minus TC over TH, or we can write this in a different, this is perfectly fine, or we can say it's the difference. We can rearrange this, multiply by TH over TH, right? So 1 is equal to TH over TH minus TC over TH, and so we'll get TH minus TC over TH. Right, so either of these is useful. So one interesting thing here is that we get an expression for the efficiency of an engine that it only depends on temperatures, right? It only depends on that hot temperature and that cold temperature. And the other thing to see is that the bigger the difference between TC and TH, the more efficient the engine is. And the closer they are to each other, the less efficient it is. So just as an example, so say we have TC is room temperature, 298 Kelvin. We can compare two different values of TH. Say TH is like 350 Kelvin versus maybe like 1,000 Kelvin. And what's the difference in our efficiency in those cases? Okay, so for 350 Kelvin, we get that the efficiency is equal to 1 minus 298 over 350. The Kelvins cancel. So this will be something as a percentage, it'll be something less than 1. All right, so let's go ahead and pull up my calculator. All right. So we get 1 minus 298 divided by 350, which is only 14.8%, 14.9%. So not very efficient. If we repeat the same calculation at 1,000 Kelvin, we'll get 1 minus 1,000 divided, 298 divided by 1,000. That should give us a higher efficiency. So we'll just repeat this, replace this with 1,000 here, and we get 70% efficiency. So see a pretty drastic difference. The bigger the difference you can get in between TC and TH, the much more efficient your engine will be. And so now I will say this is a theoretical ideal. This is the maximum possible you could get because this assumes you do everything reversibly. In a real engine, you don't do things reversibly, right? You explode your fuel-air mixture and your piston moves irreversibly. It's not this gradual maintaining equilibrium all along. So you'll always have losses due to friction, etc., that will decrease the efficiency. So this is the maximum possible efficiency, but the actual efficiency you'll get will always be less than this. Another thing that we can find from this is that if our temperatures are equal, right, if TH and TC are equal, we can't do any work at all. Right, our efficiency goes to 0. That's just another way of stating the second law of thermodynamics. So that's it for our chapter 20 on entropy.